So what I want you to do is, I want all of you to go to your My ASU, go to Robotics 1, and in Robotics 1, I want you to go to Modules, and in Modules, I want you to download the files. So I'll share my screen. So I want you to go to Robotics 1. I want you to go to Modules, and then I want you to actually expand Fall 22. And in Fall 22, as you go down, I want you to download this Robot Dynamics 22.raw. And this is called as a RAR file, which is again a compressed file. So you will have, if you don't have a software to download RAR, then you can actually install this free software. It's called as WinRAR. So you can download WinRAR and expand that file. Everyone understood? Go on to the canvas, go to Robot Dynamics 22.rar and download that and then expand it. Once you expand it, you will observe that this file has something like you would see all this. You would basically see SDOS, you would see simple pendulum, you would see double pendulum, you would see RR robot dynamics, you would see RP robot dynamics, then you will see all other robot dynamics problems. Are you with me so far? I'll give you a minute and I want you to go and download it and expand it. Are you able to download it? Expand it? Do you have this directory structure? And in this directory structure, first I want you to look at SDOF. SDOF is the single degree of freedom system. Single degree of freedom system. So what this is a simple spring mass damper system. So remember, we talked about this spring mass system. So you have mass M, you have stiffness K. This is going to be M x double dot plus Kx is equal to 0, where M is equal to mass in kilogram, K is stiffness in Newton meter. Now, what I want to do is, what is the kinetic energy of this spring mass system? The kinetic energy for the spring mass system, kinetic energy is 1/2 mv square, which is 1/2 mx dot square. What is the potential energy? Potential energy is equal to 1/2 K x square. Are you with me? What is the Lagrangian? Lagrangian is T minus V. L is equal to T minus V. Are you with me so far? Now, the MATLAB program that I have is it will take this Lagrangian, apply the Lagrangian equation, find out the differential equation of motion, and then numerically integrate the differential equation of motion and generate a plot. So what would it do is from this Lagrangian, from this Lagrangian, it will find out this differential equation of motion, and this differential equation of motion will be numerically solved. This differential equation of motion will be numerically solved, and you will have time on x-axis, x on y-axis, x dot, and time. Are you with me so far? So you don't have to solve this equation in the closed form. MATLAB will do it for you. And now for all the dynamics problem, whether it's a robot arm, if it's a simple pendulum, it's a double pendulum, it's a robot, RP, whatever type of robot it is, our job is to find out T, find out V, and substitute in the code T minus V, and that MATLAB function will derive the differential equation of motion and solve the differential equation of motion. Everyone understood this? Now, what I'm going to do is I'm going to go through that code line by line, and then I want you, if you have computer in front of you, please open this code, and I want you to follow the code line by line. And here is what I recommend. It may look easy, but when you try to implement it, it's going to give you a lot of errors. So first and foremost, as I'm going to discuss the code line by line, I want you to add comments to the code or make notes. Everyone understood this? Because we are going to follow the exact same procedure, whether it's a 5 degree of freedom robot, 10 degree of freedom robot, or 100 degree of freedom robot. Everyone understood this? Find the velocity, find the displacement, find the kinetic energy, find the potential energy, find Lagrangian, and let MATLAB do the rest. Everyone understood this? Okay. Now what I want you to do is, so first and foremost, click this code, which is example spring mass. Everyone, is this code in front of you? Okay. Now what I want you to do is, before we even do anything, let's make sure that our environmental variables are set properly, and then we can just go to editor and then click run. So I want you to run this code, and after you run this code, first it will ask you to change the directory. Click yes, and then it will run the code for some time, and then at the end it should generate a plot. Are you able to see this plot? Yes or no? Yes? Is that giving an error? What error? Oh, because you don't have a Simulink installed. I'm getting over. Yeah, morning is fine. Yeah, morning is fine. Morning is fine. You don't have a Simulink installed. That is the problem. Everyone else got it? So this is, so what it is, is in this code, I gave a Lagrangian and the MATLAB code found the differential equation, numerically integrated the differential equation. And what you see in front is time versus displacement. The first plot is time versus displacement, and the second plot is time versus velocity, or displacement versus time, velocity versus time. Online students, are you getting the results? I'm looking at the chat window. Online students. Okay, so I see the students are getting the results. So now I'm going to discuss the code, and please understand this is very important. So the example number 1 is on spring mass. Okay, so this is the system, spring and mass. Line number 1 is comment. It's just explaining what the example is. Line number 2 is defining the symbolic variables. What are the symbolic variables? First variable is the displacement. Second symbolic variable is the derivative of displacement, which is velocity. So the symbolic variables are x and xd. Are you with me? If you have a robot arm, then probably your symbolic variables would be theta, theta d, or theta 1, theta 1d, theta 2, theta 2d. Everyone understood this? The sequence is very important. First displacement, next velocity. Okay, so make that note. Next, I'm defining what is called as the gravitational constant. G is equal to 9.81. Mass M is equal to 0.1 kilogram. So that is the mass, which is 0.1 kilogram. Are you okay with me? And then K is the spring stiffness, which is Newton per meter. K. Everyone understood? And then D, which is the damping. Damping is assumed to be 0 for the time being. Everyone okay with this? Online students, everyone understood? So first I have defined the symbolic variables. Then I have defined the constant. Now the next line is super important. Again, not 7, line number 7, line number 8. Line number 8 is where the Lagrangian is defined. Lagrangian is T minus V, where T is the kinetic energy and V is the potential energy. What is the kinetic energy? Check this out. Mass multiplied by the x dot square by 2. Can you see? The kinetic energy is 1/2 mv square. 1/2 mv square. Everyone okay with this? Next, minus. What is the potential energy? K x square by 2. Do you agree with me? So this is where you define the Lagrangian. And now this is the structure that of the variable that we need to maintain, so that we can call in this code, which is Euler-Lagrange. That code will actually perform the Lagrangian analysis with the equation and give us the result. Everyone understood this? Please understand, this function requires line number 9 to line number 13 written in a very specific form. If you mess that form up, the function will not run. So this function, first, x are the variables, which are nothing but the states. Can you see the states are x and xd? Please note, I defined the symbolic variables x and xt same way I define the states. Do you agree with me? Then I have these generalized forces, which are nothing but the external forces. On this mass, there is no external force. Do you agree with me? Since there is no external force, the generalized forces are 0. Then there are these internal forces. As you can see, there are no internal forces. So internal forces are 0. You agree with me? Then R is basically the damping, but damping is given as d times xt square by 2. But since our d is 0, you can, for the time being, you can write r is equal to 0. That's totally fine. You can just write r is equal to 0, that is fine. And there are no external parameters. External parameters means if you have to pass some parameters, for example, if your mass is changing with respect to time, then that is passed on as the parameter. So there are no parameters. That's why it is empty. Vf, which is the function, for that we need to call this Euler-Lagrange, and then you have to specify this. This will remain as is. So for every function, every dynamic robot or any robot dynamics or any multi-body dynamics, line number 16 is going to remain as is. L, X, Q, I, Q, E, R, M, S, and ODE2. Everyone understood this? Once you run this, at the end, it's going to generate something called as VF. And this Euler-Lagrange, for that, I want you to open this MATLAB function. Can you see the MATLAB function here, Euler-Lagrange? Open this MATLAB function. This MATLAB function is given by the MathWorks. And this function, what it will do is, it will derive the system differential equation based on the Lagrangian. And this first few lines gives you the script. It also talks about the format of the function. So derives the system differential equation based on the system Lagrangian. L is equal to T minus V, where T is the kinetic and V is the potential energy of the system. And the beauty of this function is, it will not only create a MATLAB function that it can be used, it also creates a Simulink block that we can use for analysis. So it not only creates the MATLAB function, but it also creates the Simulink block. Everyone understood this? So how would we go about it? If you look at the help, it will show you. So when you run, just don't add S, just do N. It will, you don't have Simulink, so you don't add this S, just add M, and then it will work. So if you go down, this gives you the help, and there are some examples. Example 1, example 2, example 3, example 4, 5, and so on. So, but what I want you to do is, so once VF is done, it will generate a MATLAB function which is called ODE2.m. Can you see ODE2.m is the name of the function? So please note, there is a MATLAB code ODE2.m and then ODE2 underscore block.slx. So basically that created a Simulink block. So you have a MATLAB function, and then you have, yeah. What? So yes, if we have a robot with the damper, then we will add some damping coefficient. But right now, in this particular problem, we don't have a damper, so we are ignoring it. And actually, we can, if you want to run this code in the next iteration, what I want you to do is, I want you, so D here I specified as 0. You can specify the value of D as 0.1 or 0.2, and you will see the response of the system. Everyone understood so far? Okay. So what I want you to do is, now let's look at the ODE2.m function. ODE2.m function is where that code is entered. This is basically the differential equation converted into first order form. So this is the differential equation that is converted into the first order form. So as you can see that this function is of the form, this is the state space form, d by dt is equal to y and y multiplied by this constant. So once again, please understand, whenever MATLAB tries to write the differential equation, MATLAB does not numerically integrate the differential equation in the second order form. Can you see there are two dots, which means this is the differential equation. The order of the differential equation is 2. For MATLAB to numerically integrate using ODE45, ODE23 or any other solver, this differential equation must be written in first order form. So how do we write the differential equation in first order form? So please understand, x double dot is equal to minus k by m x. Do you agree with me? X double dot is equal to minus k by m x. This is the same way I have written this differential equation. Do you agree with me? Now, so what I'm going to do is, I'm going to write this differential equation is dx by dt is equal to so I will write this slightly differently. So I have states x dot d by dt is equal to so this will become 0, 1 minus k by m 0. Do you agree with me? And this equation is in the first order form, and that is the equation that is shown over here. Can you see dy by dt is, you can see x2 and minus k by n, which is nothing but y1 multiplied by this constant. Can you see this is k minus k divided by n? Everyone understood that? So that equation in the first order form is coded over here. Any questions from my online students? So next, what you do is you will go to the second part. So line number 20 is pause for 20 seconds. And the reason this pause function is added, because MATLAB takes some time to form those differential equations of motion. So MATLAB takes some time to form those differential equations of motion. That's why you have pause 10 seconds. Then for numerical integration, you have to specify the time span from which time to which time you need to perform integration. So I would like to perform the integration from time t is equal to 0 all the way to 10 seconds. Everyone understood this? 0 to 10 seconds. Then the initial conditions are 0.1, which is the displacement, 0.1 is the velocity. So initial displacement is 0.1, initial velocity is 0.1. Do you agree with me? Then I'm using this function ODE113. This is the standard MATLAB solver You can use ODE 23, ODE 45, or any other MATLAB solver. ODE 113 is one of that. Remember, our equation is written in ODE 2.m. That is the name of the function where my equation is written in the first order form. Everyone understood this? So the input to this function is at the rate. This is the function handle. So basically ODE2 is where the differential equation is. T-span, where we define the T-span, and then Y0, which is the initial condition. Everyone understood this? So what this line number 26 will do, it will perform the numerical integration on the first order form that we solved. Everyone understood this? And then the next part is I'm creating these plots. The first plot, in case if you are wondering, the syntax for subplot is subplot 2 means there are two plots inside one plot. First, and first, second. So first row, first row, second column. So there are two plots. This is the first plot, which is T, Y. So time is on the x-axis and Y, which is the displacement, that is on y-axis. Everyone understood this? Here, again, subplot 212 plot, time is on x-axis and velocity y2 is on the y-axis. Everyone understood this? So now when you run this code, you're gonna get the first plot, which is the displacement, and the second plot, which is the velocity. Everyone understood this? Yeah.
So for the language, we have the formula of del L del theta dot and that formula. So using that formula, we are finding the dot and the force of the different points, right?
So the beauty here is, once you define the Lagrangian L T minus V, you don't have to do anything. MATLAB will do that differentiation for you. It will put the equation in the first order form and you can numerically integrate and find the solution of the differential equation. So remember all that stuff that we used to do, you don't have to do it anymore. Everyone understood this? Now I want you to quickly try this value of D instead of 0, say 0.1. Try the value of 0.1 and run. So try running the code and see what result you get. And please understand, this result shows the response of the spring, mass, and damper system. Are you with me? Are you able to get this result? Okay. Online students, any questions? Now, one thing I want you to observe, and if you don't have Simulink, you won't be able to see it. But if you have Simulink, you will be able to observe it. So double click on ODE2 block SLX. Please double click on ODE2 block SLX. This is the Simulink block of the differential equation. This is the Simulink block of the differential equation. Now, what that means is I want you to double click on this block, and this block will basically that encapsulates the MATLAB function. So what you have done is you have taken that MATLAB function and wrapped it in the Simulink wrapper. So now you can use Simulink to run this MATLAB function. So now you can use Simulink to run this MATLAB function. Now, how would we perform the integration in the Simulink? So for that, I want you to go to answer. And here I have given you the solution. Click on ODE block SLX. Unfortunately, that is open. So MATLAB will give an error. So close this and open this ODE block SLX. Go to answer. Open this ODE block SLX. And now what I want you to see is, I want you to see the integration in the Simulink. I want you to see the integration in the Simulink. This is the same block that was constructed by that function. Now, time, you need to ground it to the system time, which means the simulation time should be same as the block time. So what I want you to do is, I want you to add a ground. Then here, this is the first order differential equation, which means you will have to integrate only once for the solution. So as you can see, there is only one integrator. You take this dy dt, perform one integration and feed the solution to the scope, and then tap it from here and take it back. Now the next question is, where would you add the initial conditions? So initial conditions are added in the Simulink block. Can you see the initial conditions are 0, 0.1, 0.1. So what I want you to do now, and I want everyone to work with me. So go back, open up ODE2 block SLX. This gives you the block. Are you with me? This gives you the block. Go to the library browser. And then go on to ground. So grab this ground from here, place this over here. Then what you want to do is, you want to go on to integrator. So go to library, Simulink, commonly used blocks. And then I want you to go to integrator. Grab the integrator from here. Connect it over here. So in scope, add the scope over here, and this Y, drag it and connect it over here. Are you with me so far? This is how it looks. And then we can run. But now you will notice nothing will happen, because what that means, so you need to provide the initial conditions 0.1, comma 0.1. And if you double click, you can see the code. Are you with me so far? If you don't have Simulink, this will not run. See, you install. Now is it running? Okay. Yes.
What was it that you said you had done the integrator? You had to-
Yes, I'll show it to you again.
Thank you.
So this is the function. Then I added the integrator block from here. Go to Simulink, commonly used functions, drag and drop integrator. Then if you want, so you need to specify the initial conditions. Remember in the MATLAB script, when we ran the script, the initial conditions were 0.1 displacement, 0.1 velocity. So where would you add the initial conditions? So you need to double click this integrator block. And can you see initial conditions here? This is where you want to add the initial condition. And once you run it, you get the answer. Just for the kicks, make these initial conditions 0. Make this 0 and make this 0. What would happen? Nothing. Just try that. Just make both the initial conditions 0. Yeah.
For the sign, the inertia in all directions will be different, right?
No, we are not there. So one thing I want to tell you that those assignment problems are a little bit out of set. So I'm gonna give you some extension. So which assignment you're talking about? Fourth one, right? I will give you an extension. That material is not covered yet.
I think your last, concept for that.
Yeah, so that's very good. Wow. You use your spring break very wisely. Thank you. But that I haven't discussed that material. So everyone understood this? Because I haven't talked about the moment of inertias in 3 dimensions and all. We are not, right now, we have not talked about it. Okay. Now what I'm gonna do is, I'm gonna do the next problem. Everyone understood? All my students, online students? Were you able to get the results? I'm looking at the chat window. Can't see equation on the board. Okay. I don't know. So these are the equations. Okay. Are you able to see the equations now? Okay. So everyone got these results? And please understand the equation, the ODE2 is implementing this equation, which is the first order equation. But please understand, we did not do anything. We only supplied Lagrangian and MATLAB did everything else. So now what I want to do is, I want to use the same approach to solve the pendulum problem. So what I want you to do is, I want you to go back and I want you to open up simple pendulum. I want you to open up simple pendulum. Do you want me to derive the Lagrangian for the simple pendulum? We derived that in last class. Remember simple pendulum? Okay, so I'm gonna jump directly onto the code. So go to this code, equation, run this first. Equation, run this first. And this equation is for undamped pendulum. And we are gonna go to the same thing. First, line number 1 is the comment, example 3, which is undamped pendulum. Line number 2, I'm going to define the states. For pendulum, a simple pendulum, what are the states? Theta and theta dot. Angular displacement and angular velocity. Are you with me so far? So that's why I have symbolic variable TH stands for theta and THD stands for theta dot. So theta and theta dot. Everyone with me? Now, next, I'm going to define the constant. For the simple pendulum, what are the constants? Constants are the gravitational constant 9.81, mass 0.1 kilogram, the length of the pendulum is 1 meter, and the damping for the pendulum, there is no damping, so K is equal to 0. Are you with me? These are the values. Gravity 9.81, x is equal to 0.1, L is equal to 1, K is equal to 0. Now, what I want to do is, I want to write the Lagrangian, and this Lagrangian is given as 1/2 m L square theta dot plus m GL cosine theta. Now please understand, and I don't know if you remember. Can I erase this? Online students, I'm gonna erase this and then just write down the pendulum equation. I'm gonna erase this quickly. So basically, this is the pendulum. This is L. This is theta. Theta dot. So kinetic energy is equal to 1/2. This is m L square theta dot square. And the potential energy, this is the datum. And as you can see, this is L cosine theta. is minus mg L cosine theta. Are you with me? So this is T V and L is equal to T minus. That's why the Lagrangian here, online students, please pay attention. That's why you have a positive sign. Are you everyone okay with this? Online students, can you see my screen and equations? Yeah. So this negative becomes positive here. Okay. Okay, so now, okay, now what I want you to do is, please see that I have this Lagrangian. Then on the next line, which is line number 9, I have variables or the states TH and THD. It is very important that the sequence of symbolic variables should be repeated. Are you with me so far? Otherwise, this Euler-Lagrange function may or may not work. Qi are the external forces or generalized forces. There are no forces, that's why 0. E is the internal forces, no internal forces, 0. Value of K is 0, no parameters. So now I'm going to use this Vf is equal to Euler-Lagrange. Everyone understood this? And I want you to understand this function prototype or the way we call the function is going to remain exactly the same. You will say Vf is equal to Euler-Lagrange L, X, Qi, Qe, R, pan. This sequence has to be the same. You cannot just change the sequence. Everyone understood this? The only thing that you can say here is you can have n and you can have a blank here. If you don't have anything here, then Simulink file will not be created. But M means create a MATLAB file, create a Simulink file, and this is the name of the file that will be created. Everyone understood this? So what that means is ODE.M will have the actual equation in the first order form. ODE1 underscore block that SLX will have the Simulink function that we can integrate. Everyone understood this? Now the next part is if you go down a little bit, you need to provide a pause because it takes some time for MATLAB to process this. So you cannot, if you remove the pause, then before actually going to the next step, MATLAB will get stuck. And then again, I'm supplying the time span. Time span is from 0 to 10 seconds. So initial time is 0, final time is 10. The initial conditions are the displacement is 0.1 and velocity is 0.1. Everyone understood this? Displacement, which is the angular displacement, is 0.1. Angular velocity is 0.1. It is extremely important to understand MATLAB by default, the unit of angle is radian. So the initial condition here 0 is 0.1 radians and 0.1 radians per second. Are you with me so far? So 0.1 radians and 0.1 radians per second. Then I will perform the numerical integration t comma y ODE113, name of the function, t span, and all the initial conditions. Everyone understood this? And then same thing. How many states do I have? I have 2 states. What are these states? The states are angular displacement, angular velocity. So I'm going to plot angular displacement versus time, angular velocity versus time. The first plot is going to give me angular displacement But please understand, the output is in radians. I want to plot it in degrees, so I am multiplying by 180 and dividing it by pi. Velocity again is in radians per second, multiplying by 180, dividing it by pi. So I got the answer. Everyone understood this? Please run this code and see what answers you get. Any questions? And then just generate those plots. And what I want you to do is I will give you 2 minutes. I want you to double click on ODE block.slx, ODE1 block.slx, and this will be the block. Quickly construct the integrator around it. So what you are going to do is add the ground block to T, then add an integrator, grab the integrator, and then so basically go on to the library, Simulink, commonly used blocks. Then I want you to go down, get an integrator, grab an integrator from here. Grab an integrator from here, connect this integrator, grab this ground block, then what you do is get this scope, plot it over here, grab it over here, and then grab it from here. And then where do you supply the initial conditions? Initial conditions will be supplied here. Are you okay? Online students, are you able to follow this? And then I want you, okay. Then what I want you to do is just quickly run this code and double click on here, and you should be able to see. You can see you have initial condition and you have velocity. Displacement is yellow and velocity is blue. The only difference between this plot and the previous plot is I did not multiply the plot by pi by 180. Are you with me so far? So that's why you can see the initial condition is starting at 0.1 radians per second and 0.1 radians. Everyone understood this? Everyone comfortable with these two problems? Can we go on to more difficult problems now? So what will happen when we are trying to solve a robot problem? The first thing what we are going to do for robot problem is we are going to solve the forward kinematics equation. We are going to solve the forward kinematics. After we are done with forward kinematics, we will know the position of the end effector. Everyone agrees? We know the position of the end effector. What we will do is, based on that position equation, we will find out the velocity of the end effector. And then what we will do is, we will find out the total kinetic energy of that robot. For example, if that robot has two links, then we will find the kinetic energy of the first link, and then we will find out the kinetic energy of the second link. Then we have to find out the potential energy. So we will find out the potential energy of the first link, and then we'll find out the potential energy of the second link. So at the end, we will write our Lagrangian as the total kinetic energy minus total potential energy. Everyone understood this? So total kinetic energy minus total potential energy, and then we will code that Lagrangian inside our MATLAB script. Now, this may look complicated, but please try to understand. We have done all this. Remember the MATLAB scripts we wrote to find out the forward kinematics? Remember the MATLAB scripts that we wrote to find out the velocity of the end effector? To that same script, we are going to append this Euler Lagrangian, and which means your robot will be solved from start to end in one shot. Everyone understood this? So now I'm going to write down the steps for analyzing the robot. So online students, I want you to follow the steps that I'm going to write on the board. I would actually show you a problem. We will not actually solve the problem because I want you to be a little bit more comfortable. So try to look at the examples we talked about, and in next class, we will actually solve robot problem. So here are the steps. First, draw kinematic diagram. Then perform forward kinematics. Then find out the velocities for find kinetic energies for each mass and link. Now, one thing I want you to keep in mind, that you can have the kinetic energy of translation, and we will discuss this in detail, so don't worry about it. And you can have kinetic energy of rotation. So there are two types of kinetic energy. Find kinetic energy of each mass and link. Then fifth, find total kinetic energy is equal to T. Then six, find potential energy for each mass and link. Then seven, find total potential energy. 8, and then you find the Lagrangian is T minus V, and then use MATLAB. Okay, online students, are you able to see all these steps? Why there are slight sharp peaks? Because we did not adjust the integration. So what you want to do is, if you want to basically adjust the links, so go to model settings, and then you can tune the integration parameters. So solver details, so fixed step, auto, fundamental sample time 0.001. Okay, and try to run this code again, and oops, I made a mistake, and hopefully you can actually go to simulation, and then hopefully you will get the solution much smoother. So please try, and then you will get the solution much smoother. Those sharp peaks are because the integration time is big. You adjust the time step, the integration time is small, and then you will get a smooth feedback. Okay, any other questions from anyone? Everyone understood? Online students, can you see all these steps? Okay. Now what I want to do is, I'm not going to solve this problem, but I'm just going to give you the flavor of this problem, how you would solve a robot problem. And in the next class, we will actually work out these robot problems. So the first simple robot is RR robot. RR robot is simple revolute joint and revolute joint robot. If you recollect, the revolute joint times revolute joint robot is, can I erase this? This is the very first robot that we solved. And we solved this robot multiple ways. So you have something like this. And what we are assuming for the very first problem, we are assuming that these links are L1, L2, and this mass is N. So what we want to do is, we have to find out the kinetic energy. So if you think about it, I can show this is something like this. So this is mass M1, this mass M2. So you have mass M1 here, mass M2 here. So what I want to do is, I want to find out the kinetic energy of the first mass, kinetic energy of the second mass, find the total kinetic energy, which is kinetic energy 1 plus kinetic energy 2, and then find out the potential energy of the first mass and the potential energy of the second mass, potential energy 1, potential energy 2, and then find the Lagrangian as the total kinetic energy minus total potential energy, and then use the MATLAB tool. Now, here, what you see is I have derived the equation for the kinetic energy of the first mass, T1, kinetic energy of the second mass, potential energy of the first mass, potential energy of the second mass. So total kinetic energy T1 plus T2 minus V1 plus V2. That is how the Lagrangian is formed. Everyone understood this? And once the Lagrangian is formed, in the next step, what we do is we just call the Lagrangian function. The only thing that different here is now there are two masses. So there is theta 1d, theta 2d. So can you see theta 1d, theta 2d. So you have velocity displacement for the first mass, velocity displacement for the second mass, and then there are two forces, both of them are zero, two internal forces, zero, and then we call this Euler Lagrangian function. And now we have four states: theta 1 dot, theta 2 dot. So we plot all these four. But again, I'm gonna go line by line. I'm going to derive the kinetic energy equation for the first mass, kinetic energy equation for the second mass. We will actually work out this problem. And then there are quite a few robots that I would like to discuss. There is an RPR, there is RP, R90R, and then R90R with cylinder rod. So we will actually go through all these robot dynamics problems. And at the end, what I want to show you is I want to show you how you can actually import a robot configuration inside the MATLAB and solve. So think about it like you create a CAD model of the robot. Okay. You import that CAD model inside the MATLAB and then analyze the forward and inverse kinematics, everything in MATLAB. So we will discuss this, and at the end, we will show you how to do it on an actual physical robot. With that, I'm going to stop here. If there are any questions, I would be happy to answer. Otherwise, I will see you next week. Also, I will be teaching a semiconductor robotics course, and I want all of you to come to that class because so far you have been working with articulated robots, not the collaborative robots, but I want you to work on the collaborative robots as well. With that, I'm going to stop here and then I will see you next class.